Good morning, friends and dear students. It gives me immense pleasure to be here again for my new course, Flight Mechanics, and this is my first class for this course. So, in this, as you know, I am Dr. Yagya Dutta Dwivedhi, Professor, IIRE, Hyderabad, from Department of Aeronautical Engineering, Institute of Aeronautical Engineering. Today's my topics are basic aerodynamics, lift and drag theories. So I will be covering these topics, and so be tuned for this. I am going ahead with this topics. So in this, the topics will be introduction and the history of aeronautics, then airfoil, what is airfoil and how many types and how we can designate, theories of the lift and the drag and types. These things I am going to cover in the next 30 minutes of my today's lecture. So, introduction. If you see about the introduction, what is the aircraft? First we have to see that aircraft. An aircraft is a vehicle that is able to fly by gaining support from the air. It counters the force of gravity by using either static lift or by using the dynamic lift of an airfoil, or in a few cases the downward thrust from jet engine. So the aircraft which should able to lift up by the action and the reaction of the air. This, how to get up or how to go up, it is has to counter the weight or the mass. It is called the gravity, and this can be either by static lift or the dynamic lift of an airfoil, or the some cases the jet of the aircraft is impinging downwards and aircraft is moving upward. So like this, we have some different types of aircrafts, like an airplane, fixed wing aircraft, then helicopter, it is a rotary wing aircraft, and the other is machine capable of flight. This is the your fixed wing aircraft, this is the airplane, and this is the helicopter, and this is the ornithopter, fixed wing aircraft, helicopter, and this is the ornithopter. So here it is a flapping wing. This is the flapping wing. So this we have to ensure that aircraft is, and here these rotors are moving, and here it is fixed, wings are fixed. So it is known, so it is due to speed of the aircraft, the lift is generated by this airfoil. Every wing has the airfoil which is like this. Here also we have the, here everywhere we have the airfoil. So these airfoils are used, and these airfoils are generating the lift, and that lift has to counter the gravitational force, that is the weight of the aircraft. So before I go further, we should also have who has invented the aircraft and who are the main responsible for development of airplane, especially the fixed wing aircraft. It is known as the airplane. So control and stability of aircraft. Wright brothers' achievement was to find the mastery of the three main areas which required by functional airplanes. These are the lift, propulsion, and the control. And these are the two brothers. One is the Wright brother. This is the Wright brother with the mustache like this, and another is Wilbur. So these two brothers, basically they are the cycle mechanic, and they have flown the first aircraft in Kitty Hawk 1903 December, 3rd December 1903. They have flown this one. It is called the Wright Flyer 1. So first two in this lift and the propulsion had been studied by many researchers like Sir George Cayley, Otto Lilienthal, Octave Chanute, and the Samuel Langley. But the third one, the bigger innovation of Wright brothers flyer was control system. That is this third one. This, the main credit goes to these two brothers. So control were developed by these two brothers. And in the flyer 1, they have used and they have installed this control systems like we have today, but they have not used that horizontal tail, which is nowadays we are using behind. They have used the canard. The horizontal is in the forward of the wing. Forces acting on the aircraft. So before we start, we should also understand what are the forces. Forces we can divide into the two groups. One is aerodynamic forces, that is the lift. Then we have the drag. Here, if you see in this diagram, the vertical forces are the weight here, and this weight has to be countered by this lift. Then we have to generate the velocity of this aircraft to take off. So a drag will be generated. This drag has to be countered by the thrust. So lift is equal to weight and thrust is equal to drag for any in cruise condition. It is cruise condition. Another type of forces we can write as a non-aerodynamic. They are the weight and the thrust, as shown in this diagram. Now I will discuss about airfoil nomenclature, how the airfoils are made and how they are called and how they are identified with their different parameters. So the first diagram is here. So here, if you see here, we have here alpha L naught. We have 1, 2, 3, 4, 5. So this one is the zero lift line. This is the dotted line. This is the zero lift line. Then 2 is the leading edge. This is the leading edge of this airfoil. 3 is the nose. This circle is a nose. It is called the nose circle. 4 is a maximum camber. This, where you have the maximum distance from top to bottom, it is called the maximum camber. Maximum thickness. 5 is the camber. This is the distance from this line to chord. It is called the maximum camber. 6 is upper surface. 6 is upper surface. 7 is the trailing edge here. This is the trailing edge. 8 is camber line, mean camber line, and 9 is lower surface. So this 1 to 9 is very, very important. Zero lift line, then leading edge, the number 2. Number 3 is your nose circle. Number 4 is maximum thickness here. Then 5 is your camber of this airfoil. 6 is upper surface. 7 is a trailing edge. 8 is lower surface. 8 is here mean camber line, and 9 is lower surface. So now here we can see that 1 and 2. 1 is the chord here, which is defined as the line, straight line passing from the leading edge to the trailing edge. This is called, I write leading edge LE, and this is the trailing edge TE. So the line which is passing from leading edge to the trailing edge is called the chord. And if you see here in that, we have number 2 is a camber. If you see in this figure, from leading edge to this green line is your chord line, and this red line is the mean camber line. So this is number 2 is called the camber of this wing. 3 is the length. This green is the total length of this, and 4 is here. If you see, it is a mid line. It is called mid line. So these 4 line 1, 2, 3, 4. We have to understand that first one is the chord here. Then we have the camber here. Then we have the length here, and then we have the midline. These things. Now, if you can see here that the A is a blue line here. This blue line is a chord line. Green line is the camber line here. This is the camber line, I will write camber line, and this is the chord line. If you see the figure B here, this is called the leading edge. This is called the leading edge here. Leading edge radius, and C is XY coordinate. XY coordinate for the profile geometry. Chord is equal to x-axis and y-axis line on that leading edge. So y is here, and it is chord is always taken as a x-axis, and it is called the 1x or 1.0. So like this we can identify the things. Now a very important terms is coming, airfoil, or sometimes we say aerofoil. Airfoil is American English and aerofoil is a British English. If you see old books, there used to be aerofoil, but now if you see most of the books, they are airfoil. So both are correct, but if you are using the American language, you use the airfoil, and if you are using the British language, you use the aerofoil. So that is the difference between airfoil or airfoil. Both are the same, but their spelling is a little different. An airfoil or aerofoil is the cross-sectional shape of an object whose motion through a gas is capable of generating significant lift. So airfoil is a cross-section. If you take the wing, okay, this is the wing. So if you cut from anywhere, you will get like this. So this is the cross-section, and it is known as the airfoil. So if you move this thing in the air, which will generate the lift. So the purpose of airfoil is to generate the lift. So that is why we use the airfoil from in any of the aircraft, the wing, the tail, the vertical tail, this all are made as per the airfoil. Initially, this airfoil were designed and made by the NACA. NACA stands for the National Advisory Committee for Aeronautics and so it is airfoil. If you see here, the NACA airfoils are airfoil shapes for aircraft wing developed by the National Advisory Committee for Aeronautics. We have two types of airfoil. One is a symmetrical airfoil, another is a cambered airfoil. There is a difference between symmetrical airfoil and the cambered airfoil. Symmetrical airfoil, the both, if you take from upper side and the lower side, both will be same. This is a symmetrical. If you take this is the cambered. Means this is the chord line, and here is the chord line from like this. So upper side and lower side will be different. It will not be same. So this NACA have the different types of specification. I am discussing about here one type of this specification of the airfoil, that is called 4 digits series of airfoil. So this you can see here that what is the airfoil, and if you see here, from this is the leading edge and this is the trailing edge, and if you join this thing, it is a chord. This is the chord. Okay, so like this. So the NACA 4-digit wing section define the profile by first digit describing maximum camber as percentage of the chord. So suppose there are 2412. This is the NACA series 2412. So the first digit describing maximum camber as percentage of the chord. So here this 2 indicate that 2% of chord is a maximum camber. Maximum camber means the camber location will be 2% maximum. Then we will go for the next. Second digit describes the distance of maximum camber from the airfoil leading edge in 10th of the chord. So it is means the here is a 4. This 4 indicates that this 2% is falling at 40% from here. 40% from the leading edge. That is the indication of this number 4. And the last 2 digits describing maximum thickness of the airfoil as percentage of the chord. So this 12 means the maximum thickness is 12 percentage of the chord. Means if it is 100 millimeter, 12 millimeter is the maximum thickness, 2 millimeter is the maximum camber. So for example, I have discussed here. So same way we have to further see here that, for example, the NACA 2412 airfoil has a maximum camber of 2%. Just this is the 2%. So maximum camber is 2%. If the 40 means it is located at 40% or means 0.4 of the chord from the leading edge with the maximum thickness of 12%. So that is the meaning of 2412. But if it is the symmetric airfoil, the NACA 0015 airfoil is symmetrical. The 00 indicates that it has no camber. The last 2 digits, that is 15, indicates that the airfoil has 15% thickness to chord length ratio. It is 15% as thick as it is long. So if it is NACA 0018, so what is the meaning of this? 00 means it is symmetric airfoil. Symmetric airfoil, and 18 is the 18% of chord length. If 100 millimeter is the chord length from here to here, this is the 100. If this is the 100 millimeter, so your maximum thickness will be 15 millimeter, and this location will be, it is at 25% of the chord, because it is 1 by C by 4. It will act at C by 4. So that is the beauty of this airfoil, how to recognize and how to, by the number you can understand that how much is required for this. Now I will talk something about the lift, because as of now we have seen that the airfoils are used to generate the lift, and how this lift is produced, it is some equations are required. You can see here one aerofoil, and in this airfoil the lift is equal to CL into half rho V square into A, where CL is a coefficient of lift which contains all the complex dependencies and is usually determined experimentally through the wind tunnel. Rho is the density of air, V is the free stream velocity, A is your wing area, and it is divided by 2. So that is the lift equation, and it is shown in this diagram. Now, contributors in lift. Who all are the people who have developed this theory of lift? So here I will be talking about these all theories. So here we have the Daniel Bernoulli. He is the one scientist who is responsible for doing this thing. So this Daniel Bernoulli is the main person who has developed the relation between the pressure energy and the kinetic energy. Then very renowned person, Sir Isaac Newton. These two people are very important person, but we have some more like Kutta, Joukowsky and all. Their theories are nowadays very much applicable. Oh, we will see the Bernoulli's equation. What is the Bernoulli's equation? In this we have some restrictions on this, some assumptions like the fluid should be inviscid, steady, incompressible, no heat addition, negligible change in height. P is equal to pressure, V is equal to velocity, rho is equal to density. These are the few parameters which will vary in this channel. We know that along the streamline from 1 to 2, the static pressure plus dynamic pressure is equal to total pressure. So static pressure is denoted by PS here, and the dynamic half rho V square is equal to total pressure, or we can write at 1 and the 2, PS plus half rho V square at 1 is equal to PS plus half rho V square at 2. Means the total energy, pressure energy at 1 will be same as total energy at 2. So actually this Bernoulli equation is nothing but it is a conservation of energy. So this is the law which relates pressure into velocity. That is the contribution, and this principle is used very much significantly on airfoil lift generation. We should also see the second one is Newton's third law applied to the aerodynamics. We know the Newton's third law, for every action there is an equal and opposite reaction. This you can see the airfoil here, the flow is moving from this direction. As and when it is touching here, the flow is moved like that, and here it is start downwards. It is called downwards, and this will give the flow direction like this downwards, and this flow direction, due to this, a force of reaction will act in this direction, and this is called the lift force. This is the lift force which is generated by reaction of this action. This is the action and this is here reaction. Next we can see here that if you are, one ball is there and the flow is moving downwards like this, same way here, this is the action because it is moving downwards. There will be reaction in upward, and this is called the lift. This is the lift. Ball deflected up. This ball will move in this direction. If you just spin ball like this, ball will go like this. Means as per your rotation, the ball deflection will change, and it is happening due to the action and the reaction process by the Newton's third law of motion. For the jet engine, for the rocket propulsion, we use the action and the reaction and this we all are aware about that. Now I will discuss about lift theories, and in this we have first lift theories, longer path or equal transit theory. Longer path or equal transit theory. So how it is working, this we can see here that two molecules, one is the blue, another is a red, both are moving together. As it is just about to this leading edge, one molecule of blue is moving upward, another molecule is moving downwards. So the upper surface, the molecule which is upper surface, that is the blue in color, because this both have to reach in the same time here. So if you see here, upper side, due to the curvature, it has to travel more distance in the same time. Below it is less distance in the same time. Upper surface velocity will increase. Upper surface acceleration will be generated. Lower surface it is not generated. So there is a pressure difference between lower side is high pressure. This is the high pressure, and in this side it is low pressure. So there is a net pressure, pressure lower minus pressure upper. This pressure lower minus pressure upper will give a delta P, and this delta P into the area of the wing, this is called the lift. So in this way lift is generated as it is shown in this diagram. So top of airfoil is shaped to provide longer path than the bottom. Air molecules have farther to go over the top. Just now I have explained you. Air molecules must move faster over the top to meet the molecules at the trailing edge at the same time. From Bernoulli's equation, higher velocity produces lower pressure on the top. Difference in pressure produces the lift. So just now same thing I have explained here, and we have got this theory 1, longer path, and the equal transit theory. Next I will Another theory is there, skipping stone theory. In this, if you hit something, it will hit and it will change its direction. So there is a change in momentum, and the rate of change of momentum is a force by the second law of thermodynamics. So lift is the result of the simple action and the reaction. As air molecules strike bottom of the air, imparting momentum to the fire. If you can see here, that is the inflow. It is hitting the red and then it is reverting in this direction. So there will be a resulting force in upward direction, and this is called the lift force. And it is due to the skipping stone action and the reaction by the Newton's third law is applied in this also. Next theory is the Venturi theory. It is also related with the Bernoulli only, but little concept is different from the first. We have given the P and V relation. Now here area and the velocity relation and then pressure relation will come into the play. If you see, the one is the free stream here, this one from here to here, it is moving from here to here, and inflow is from this direction. Inflow is from this direction, and when it is touching the upward, if you see here, area of this, and area of this. This I am writing 1, 2, and 3. So A1, A2, and A3. So A2 is less than A1. A2 is also sorry, here less than, not this. A2 is less than A1. A2 is also less than A3. So here area is less. So the velocity here V2, V1, and V3. So V2 is more than A2, V2, V1, and V2 is also more than V3. V2 is more than V1 and V3 is also. So here the velocity is highest. So this velocity will make pressure here lowest pressure in this point. And here you have the highest pressure. This pressure difference by the Venturi system also we can explain this pressure. So we can see here that the Venturi theory, upper surface of the airfoil behaves like a Venturi nozzle, constricting the flow through the contraction. Flow speed up, velocity times area equal a constant. So A1 V1 is equal to A2 V2 is equal to A3 V3. So if the area is reducing, conservation of mass, if area is reducing, velocity has to increase. If the velocity is decreasing, area has to increase. So vice versa. Through the contraction, flow speed up, velocity times area equal to a constant, and this is equal to constant. From Bernoulli's equation, high velocity gives low pressure, decreasing pressure on upper surface produces lift. So this is the another theory. So we have covered the three theory, but if we see here, everywhere Bernoulli's equations are there, and we have seen that in Bernoulli's equation 8 assumptions are there: inviscid, irrotational, so many. If you see here, I have already explained about the Bernoulli's. So in that I have shown some 8 assumptions earlier. So those, if you see in the real, it is not very accurate prediction of the lift. So now some modern theory has come, and in this we have the bound vortex theory. This theory was developed by Kutta Condition, and they have examined that without circulation you won't get the lift. Means if you see the surface of the airfoil, the surface is like this. Air has to move like this. If it is moving like this, then circulation is generated. And if there is no circulation, like flat plate at 0, you won't get any lift, because there is no circulation. To get the lift, a circulation is required, and that is the vortex, or some circulation are called the vortex, and those vortex are very much essential to generate the lift. So Kutta has given some formulation that if flow is moving from this direction with velocity v and the density of this thing, and it is hitting some object and there is a circulation. This is the tau is a circulation. So vortex strength is tau, free stream velocity is v, air density is rho. Kutta has explained that lift is equal to rho v tau. Rho into v into this circulation or vortex length strength. And they have found and they have made this experimental result that theory correctly predicts slope of the curve is equal to 2 pi for thin airfoil. The slope of this thing will go like this. So this they have proved that this theory is 100% correct for the real scenario up to certain angle of attack. This is the modern theory of lift known as the Kutta theorem or circulation theory. So this is the modern theory and it is mostly applicable in all the field of. So just I will discuss about what is this bound vortex or the said vortex. So if you see here that lift is generated by turning a flow of the air. So flow has to be circulated like this as it is shown here. The flow turning creates a downwash, creates bound vorticity. So it is called the bound vortex here. And the existence of the bound vortex within the airfoil created an theoretical problem when it was first proposed. So he was not able to understand this thing here. Okay, so people were not believing that it is not possible. Okay, so a static fluid has no vorticity within it. By the conservation law, fluid should not have any vortex or vortices. With a bound vortex within the object, then another vortex of opposite strength must be there called the said vortex. So what is the said vortex? It is the bound vortex which is on top of the airfoil, but Kutta has found out this, but he was not aware about the said vortex. So there should be said vortex, otherwise it is not following the conservation of law. So there is one more vortex which is the same size but in opposite nature, and this was found by Prandtl experimental to show the vortex. He has done the experiment and he has found that no, there is not only the bound vortex, but there is a said vortex in the downstream of the wing. So it is a stationary fluid at rest, and this right is, this you can see, it is a bound vortex here. This is a bound vortex and this is the said vortex. So he has found by the smoke flow generation that there will be a said vortices. So his theory of Kutta was proved by the Prandtl experiment after some time of development of that theory. No vortex in fluid at rest, but clockwise it is a bound vortex and anti-clockwise is your anti-clockwise vortex is said vortex. It is a said. It is a said vortex. So in this way it was found. Now we can see the aerodynamic forces which are moving. So if you see here, if the flow is there, a force will be generated. It is in the violet color, but in the pink color it is perpendicular to this flow. It is a lift, and the parallel to the flow is a lift, green color. So it is a drag. So this is a drag and this is the lift. So drag is green, it is mentioned here, and it will be in the parallel to the flow, and the perpendicular to the flow is a lift. We can write that this F, pressure forces act normal or perpendicular to the surface. Force on the body is the vector sum of the pressure into area around the entire solid body. So this F is equal to Pn into A, Pn into dA. So lift is equal to F normal and drag is equal to F free stream in the stream. So drag is a force which is acting in the normal direction. Now we will see about the Kutta condition. Kutta condition means it should, if it is touching at the leading edge, it should leave also from the trailing edge immediately. Then there will not be any lift. So in this case, you don't have any lift. All the particles are moving in the same pace, same direction. There is no turbulence between this, no difference between upper side and the lower side. And this is the plot for that. But if there is a bound vortex, you see the shape of this thing is from the lower and it start moving like this. There will be a circulation like this. This is the circulation. This circulation makes sure that there will be a difference in pressure by the help of this bound vortex. And if you see here, the free stream and this blue is the lower surface pressure and this is the upper surface. And if you see here, this one and this one is same, but here it is not. There is this area and this area will generate the pressure and this pressure into area will generate the lift. But here no lift because it is touching the leading edge and leaving the trailing edge. Here it is below the leading edge and then only circulation will start. So that is called the Kutta condition. If leading edge and leaving and entering and the leaving in the leading and the trailing, there will not be any lift. Now I will discuss another force which is called the drag force. Lift we have discussed. Now we have to discuss about the drag. Drag is the aerodynamic force that opposes an aircraft motion through the air. Drag is a mechanical force. It is generated by the interaction and contact of the solid body with the fluid. So drag is aerodynamic force that opposes an aircraft motion. So if your aircraft is going like this, a force will try to pull backward, opposite to the motion of the aircraft. That is it is generated by the interaction and the contact of the solid body with the fluid. So it is with the fluid and with the lift also the drag is generated. For drag to be generated, the solid body must be in a contact with the fluid. There must be motion between the object and the fluid. Types of aerodynamic drag. We have the skin friction drag, we have form drag, we have induced drag, we have wave drag. So drag is countered by thrust produced by the engine and weight is countered by the lift. So this drag is produced and this has to be countered by the thrust. Okay. So to counter the drag, we should have the thrust, and to counter the weight, we should have the lift. Then only our aircraft will be able to fly. Now just I have given some concept of the lift generation again. So here if you see, this is a symmetrical airfoil. This is the case 1, and if the flow is coming and hitting here and leaving from here, there will not be any lift because flow is upper side and the lower side pressure is same, no lift. But if you give some angle of attack, it is alpha is equal to 0 here. But if you give some angle of attack, then upper side vortex is forms here, and this vortex here velocity is high, pressure is low pressure, here is high pressure. So there is a pressure difference and you will get the lift. If you see here the cambered airfoil at alpha is equal to 0 also, you will get some L is equal to some positive value. And we can draw the CL versus alpha for the symmetrical. It will start from 0 because at the 0 angle of attack, you won't get any lift. As you increase, it is increasing. And this is called the symmetrical stall of the, this is the alpha stall for symmetrical and this is the alpha stall for cambered. So alpha stall is equal to where the CL maximum you are getting. So as you increase the CL from here, as you increase the alpha, your CL will be reducing. So that is called the stall. Stall angle is very important angle, and if you are going beyond the stall, your aircraft lift will reduce and your flight will start falling down. Lift of the finite wing, if we understand that we know that lower side is high pressure and upper side is low pressure, negative pressure, there will be a circulation in this direction and this will move and vortex drag will be generated, and this is called the vortex drag, and which is lift induced drag. Sometimes we call it induced drag. From here drag, another component of drag will come. So in a wing of infinite, no vortex drag. So for a minimum drag, lift distribution should be elliptical, like this one, elliptical. But we cannot get elliptical, so we have to make a taper here. It is called the chord at the root and chord of the tip, and this is called the taper ratio. This is the taper ratio. So this is the lambda. Okay, so this lambda is equal to Ct by Cr. It is a chord at the tip and this is the chord at the root. So this lambda Ct by Cr, this value should be 0.4 to 0.5. If you have like this, so it is near to the elliptical. So you will get better drag performance. So we need to reduce vortex. That is we need some winglets, airfoil of the tip. So here we will use the winglet. So here this circulation will be reduced. So in this we need another aspect is called aspect ratio, and aspect ratio is defined as the span by the chord for a rectangular wing, but for another wing it is b square by s, where b is a span, s is equal to area. So these are the equation for the aspect ratio, and these aspect ratio are useful for the drag, prediction of the drag. Everywhere this aspect ratio will be used, especially for induced drag. Aspect ratio is one of the very important parameter. So now we should also discuss something about controls. So we have the three control. One is the elevator, another is the rudder, and third one is the ailerons. So these elevators are fixed at the tail. This is the tail, and these are your elevators. The elevators are used for pitching motion, nose up and down. So it is for pitching, because if you make up, then a force will be in the downwards direction and it will pull. So if this is the aircraft and this is your tail, and if you want nose up, your elevator should go up to this, up will generate downwards like this. If you want nose down, you have to make nose down. A force opposite direction will act. It will pull up, your nose will go down. So if you want nose up, your elevator should go up. If you want nose down, your elevator should go down, because force will act in opposite direction of deflection of any component. So in this way, your elevators are working. Next control is the rudder. Rudders are used for yawing motion, that is the nose left or the right. And here also the same way, if you want to go right or if you want to the left. So if you want to go the right, your elevator should go right like this. Then nose will go, because force will pull in this direction. If you want left, it has to go towards the left, force will be in this direction, your nose will go left. So this rudder. Ailerons are used. These are the ailerons here. These are ailerons used for the rolling motion, and the wing which is going upward, their aileron will go downward. So if this is the aircraft and this is the wing, if I want that this should roll like this, so the aileron of this left wing should go down, then only right wing will go down. So the aileron deflection and the aileron of right wing will go up. So it will reduce the lift, it will increase the lift, and your aircraft will roll like this. So this is the aileron deflection. We also use the flaps. These flaps are used here. This you can see here. It is shown by yellow color here. These are the flaps. These flaps are used especially to increase the lift during takeoff, and during landing this has to increase the lift as well as it has to increase the drag. During takeoff we go for a certain amount of limit flap, not more than 20 degree, but during landing we can go up to 30-35 degree of deflection. So as you increase the more, it will stall and more drag will be generated. So these flaps are used during landing and takeoff. During landing to increase the lift, and during takeoff it is to increase the drag. So that is the purpose of this. These are the books which I am referring. Anderson John, Fundamentals of Aerodynamics, McGraw-Hill's, Tata McGraw-Hill's, these all things. Any questions, you are welcome to ask. I feel very happy to reply. If you want any questions, you can email to yddwivedhi@gmail.com. So it will be my pleasure to reply you in this. Please be tuned for my next lecture. Very interesting topics will be coming for aircraft flight mechanics and aircraft performance. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.